Also,
yeah, looks good.
Thank you.
Thank you. Just
Very
go
well.
ahead.
Okay, thank you very much. So it's a pleasure to be here. Although I have to say that Adam was scheduled to give this talk, but unfortunately he had a mild accident before the weekend. So he apologizes for not being here. He's recovering well, and they asked me to fill in his shoes, and I'll try to do my best. So I'm going to give an update for what the Joint Physics Analysis Center is doing during probably the last year and a half. So first, this is a summary of activities of JPAC. Basically, the group started in 2013. We started with Adam and three postdocs, and some supporting students. And during that time, well, we have published a lot of papers and given talks, organized events. We even have now an scattering course, and we collaborate a lot with experimental collaborations. And I want to highlight that just a few months ago, we put in the archive a review of what the JPAC physics has been during these years. So that is a very nice summary of all the effort and all the research done, and it tries to be a bit pedagogical in some of the sections. So these are the full members. We can see some pictures that might be familiar, and there are other affiliated members. There are other people who are collaborating with us, but this is like you can call it the permanent staff. So what's the job of JPAC, of what we have decided? It's our job. So we want to identify resonances. So you can have experimental or even lattice data, which means it's data in the real axis, like cross sections, bumps, dips, and your levels. And basically, we are focusing on building reaction amplitudes that allow us to extract poles and to extract what are the complex plane singularities. Because you want to start understanding things like this. This is basically the Charmonian spectrum with all the exotics that have popped out in the last years, and both fit each other. I mean, the work on the amplitudes fits the how to analyze the data and how to extract the poles. And also, that's another step that is just to start relating all those poles, all those things that you get from the reaction amplitudes, the resonances, to the microscopic models. Then that'll start the interpretation of the states. So I'm going to talk about some research that the JPAC has been doing during the last, year and a half. I'm going to focus on the scalars in gypside radiated decay, and these are going to be just glimpses, brief summaries of what we did. Everything's in the papers in detail, so even we can in the discussion session that is going to be after the coffee break, we can talk whatever you want about this works. We have also worked on XYZ production at facilities like Gulex, facilities like the Electron Collider, or what it's now being called GLF++. And we have been working on the search for exotic hybrid, which is this is like continuation of the Pi1 extraction. And also we have been working on neural networks, but I'm not going to talk about that because I already did on Thursday. So these are the three topics that I'm going to try to cover briefly. So the first thing is, of course, like the scalars and the globals, they are very, very interesting. They are the clearest sign of confinement in pure Yang-Mills theory, which makes them extremely interesting if you want to understand QCD and the strong interaction. But they are the worst state to search in real life. And the reason is because they mix a lot with ordinary states, or they're expected to mix. So one of the things that you can actually do is look. In our case, we decided to look into the radiative decay of the gypside. That there are wonderful data from BESS3, and because this is really a gluon-rich process, and it's suspected to be one of the golden channels to search for a scalar global. So we look into this BESS3 data, and we decided to fit with the same, basically this is the same model that we use for extracting the pi1 from the compass data. This is just an n over d that is related to you build basically a K matrix and then a phase space. And then in our case, we are analyzing two waves, the S and D waves, and also these two waves are and the phase shift between them. And then we are analyzing, in this case, 3 channels. Well, the pi and KK that you have data, and then like an additional channel to account for the different inelasticities, because these two channels do not account for all the inelasticity, all the channels that are really present in these reactions. And following exactly the same kind of approach that we did for the pi1, we basically fitted those data, starting from 1 GeV up to 2.5 GeV of invariant mass. And this is the result that we are getting. You can see here the pi S wave, the pi D wave, the KK bar S wave, and the KK bar D wave. And this is the phase difference, I said, for pi and also for KK bar. And the fits are very good, and they allow us to get the poles, to get this state. So we were able to get these S wave poles, which some of them are going to be, they should be mixed with the glue balls and have glue components. And then these F2 that are, well, in the case F2 1950 is expected to be more ordinary, the 1270 also. And you may notice that, well, we have large systematic uncertainty, because what we did is you just don't fix to the model that I just showed you. You just start checking, for instance, one of the things you do is to put very different functions inside this integral, and to see how the poles move and how the results are changed. And also, this has a full-blown statistical analysis using a Monte Carlo method that it's, I mean, at this point, people should know it. It's called Bootstrap. If you want to get familiar with it, if you're not familiar with the Bootstrap, we explain it in detail in our review. And there are examples even there. One thing that you might not notice is that we don't have the F0 1370. The reason is because its main decay channel, if I remember correctly, is 4 pi, and you don't actually see this signal in this data. You don't really see it, and that's why we don't have it there. We don't have, looking at this data, you don't have the capability of looking into that state. So there's in our analysis, there's no claim regarding pole position or existence of that state. Please don't take these figures, these plots, as that we are claiming that state doesn't exist. We are just not sensitive to that state in this analysis. So the second topic that I wanted to cover is what could be the spectroscopy program at Electron Collider, and what we are talking about a bit about the JLab++, which will be an upgrade of JLab going to 24 GeV. So the good thing is that here the idea is to produce resonances using either photoproduction or electroproduction. And this is going to be a clean mode of production for these heavy quartz, especially photomonia, and also hopefully to be able to produce hybrids. The kinematic separation becomes very, very good, and we expect the facility of this kind will be able to produce tetraquarks and baryon exotics, pentaquarks, and with a wide kinematic coverage. And so, for instance, what we did was using very simple models. This is not a precision paper. What we produce, these are not precision results. These are just, we're trying to give estimates in order to decide if it is worth to start looking at these states in this kind of facilities. So, I mean, we are assuming, actually, we did like a low energy, low invariant mass energy in this vertex and high energy. In one case, we were building a model that is Regge-based, and another model that is low energy based on vector meson dominance. And in this way, we are trying to get like estimates of how many events will be produced, and if it's worth to start thinking about looking into these kind of states in a future facility. And for instance, this is the case of the X3872, which we estimated that, okay, we are expecting like 3,000 events per year in this kind of photoproduction reaction. But of course, these are ballpark estimates. They are very rough estimates. And also you have to think about what could be the possible efficiency of the detectors and all that stuff. So this is just for like a physics motivation case for this and a spectroscopy program in this kind of facilities. We also look at the Y4260, which is not great because we were getting something like 50 events per year, but the production of the Y could increase with energy. So here, amber and electron collider could be a very nice alternative, and maybe it would be possible to produce the Y, enough events of the Y in this kind of channel instead of, for instance, in the current GlueX setup. So another one is the Z3900, and we also studied this guy, getting like 1,000 events per year. That was our estimation. So basically here you have a summary, and what you see in the comparison are the events that you expect from BESS 3. So you are comparing what you could get in this kind of facility compared to what you are currently getting in a facility like BESS 3. And you can see that, well, the X could be actually a very, very nicely produced, and the Z3900 also is a possibility. We also explore the possibility of producing the X6900, also pentaquark. I mean, some of them, but for instance, pentaquarks were for the electron collider, they were not very, very promising, to be honest. And then the third piece that I want to summarize of the JPAC efforts as this discussion about hybrids that we are having, and we actually had the other day there were several presentations, and actually this is part of what Bernard was showing with new compass data, which actually he has made some of my plots completely obsolete, but okay, that's life. So we have a lot of signatures of states that are like 1- plus, and we expect to produce them. Well, the new compass data for 3 pions are going to be great to extract, to get more information on this state. Not only the one that we already, the lowest energy pi1, the pi1 1600, but also to look into the multiplets. So what Compass has produced is they have given us the parcels, and what we did for the analysis of extracting the pi1 1600 was to cut the data at 2 GeV, because there's this gap, this jump is not very convincing. So we say, okay, we are going to do this parcel analysis, and we're going to analyze only this energy region, because we want to get that pi1, and we have to think about what's the physics of this kind of that you're going to encounter. So if you're in this low energy region, you have a single radius chain. So you have a region here, and here's what you are producing the resonance. In this case, basically these low energy data are dominated by the H2 and the pi1, because we are actually looking at the P and D wave. So they are the ones that you see here. For eta pi, they are very clear. For eta prime pi, they are also very, very clear too. Very, very nice data. But what happens when you go to higher energy? You need to think about this for the following, because that guy, that pi1 1600, is the lowest level. Well, it's a candidate to the lowest level hybrid, but you want to hand down the multiplets. And if you want to hand down the multiplets, you have to go higher in energy. And then you have to start taking into account this double radius process that is happening. In this case, I'm looking at the in the Godfrey-Jackson system. This is the cosine of the Godfrey-Jackson the angle. And here you have the energy dependence of both the eta pi and the eta prime pi systems. Be careful with this figure, because this figure that I'm showing here is not acceptance corrected. So this asymmetry, until you do the acceptance correction and you do the partial expansion, that's when you really have the information that you want. So one has to be careful of saying, look, there's an asymmetry here. No, because you have to take into account the detector. But I mean, this is good enough to illustrate what I'm trying to say. So then if you go to the backward, so you see that the exchanges are actually a bit more complicated, because in the case of eta pi, well, actually also in eta prime pi, you're going to have double Regge contributions from F2 Pomeron and F2 that you see here. And also you have possible contributions of Pomeron. And why these contributions are important, this one in particular, because the Pomeron, the physical interpretation of the Pomeron is actually that you have a tower of gluons, essentially. So if you have a big glue component in your data and you are at high energy, you expect this guy to be important. You expect this guy to be completely needed. This Pomeron that I'm showing you here in red. So also another thing that you need to, also you have to see that the A2 and F2s were equal and you have no Pomeron, actually. I mean, so I mean this A2 and this F2, they were completely equal in their couplings. You will have no asymmetry, and that means you will have no exotic. So Pomeron is the one that we can link to this glue component that also mixes with to get the hybrid. So, for instance, another thing that you see is that GlueX is trying to get these results. GlueX is, and these are preliminary results from GlueX that I believe they are not accept and corrected. And if this is wrong, Sean can correct me very quickly. And there's a question of why I'm not seeing anything here. So, but probably we can see here, but here we can see an asymmetry. So this is an indication. If this asymmetry holds after being corrected by acceptance, okay, this is a clear indication of exotic components and exotic physics, and the kind of physics we're trying to pin down. So this was the low energy fit, and that you all know very well, getting false. And you can go to the talk by Koff, Bertram Koff, and also you can see the talk by Joe Dudek to get a better feeling of what happens in this low energy. But as I say, you have to keep in mind also that, and here is the tricky part. We want to study this high energy region, okay? And we want to see if there are like pi1 contributions, there are exotic contributions, and we want to use a Regge model. So the thing is that in that energy region, Regge models have the quality that they are not a number of parcel waves, a limited number of parcel waves. Regge amplitudes come from the resummation of all the parcel waves. And if you look at the parcel waves of COMPASS, they include in this energy region like 6 parcel waves. So one thing that one could do, and actually we did it in the beginning when we were doing this work, was to use our Regge model to feed the parcel waves, which is completely wrong, because you are comparing something that is a resummation of all the parcel waves to a truncated parcel wave expansion. So we thought, okay, this is wrong. Actually, we were getting a lot of inconsistencies because of doing it as I say, in the wrong way. So what we decided to do was let's take the parcel waves from COMPASS in the high energy region as not physics or not physical parcel waves, but just a parameterization of the data. So we took those parcel waves and we reconstructed the equivalent of these two plots, but acceptance corrected. And that's what you get. And by doing that, you can just go to each each one of these energy slices, energy binning, and you can reconstruct what the what the event distribution would look like. And then
5 minutes left.
Thank you. And then you can start fitting. You can decide, okay, these are the models, these are the combinations of the possible exchanges, and see which ones contribute. And let's see if we have this Pomeron's contribution. And actually what we found is that we might need, I mean, this Pomeron is more or less needed not for the eta pi channel, but for the eta prime pi. And also one thing that you can do is just you can reconstruct you can integrate from 0 to 1 in the cosine of theta and get the forward intensity. You can also integrate between -1 and 0 in the cosine of theta and get the backward intensity. And this is how they look like. You have the total intensity, and then you can get the asymmetry. You can forward minus backward, forward plus backward. And this asymmetry, and keep in mind, if it's different from 0, that means that you have hybrids, you have exotics in that in those data. You can see that the exotics are more prominent in eta prime pi, and that's what we are finding, that these Pomeron diagrams, this kind of contributions are more important and are needed. So what is the message of this? The message is that when you are in the low energy region, you can do partial wave expansion, and that is going to work very, very nicely. But when you are in the high energy region, you have to start thinking about the contribution from these double radio diagrams in order to extract properly the partial waves where the resonances are going to appear, and in order to extract what is going to be the exotic contribution. And that means that has to be incorporated in the amplitude analysis and probably in the partial wave expansions. And also, another thing that you can actually do is to start using finite energy sum rules, which means that you can just, for instance, this is for pi and nucleon, but actually these ones that I'm writing, these ones are for photo production, and these ones are for pi and nucleon, this diagram. The thing is that you can basically integrate the dispersive integral and then integrate one piece is coming from the resonances, which is the one that you see here. And then this piece that is the semicircle, you can integrate it using radius theory. And then when you do that, you can equate these two guys in order to reconstruct the whole, let's call it the whole integral. And then you can use radius theory to restrict, to constrain, the amplitudes and the physics that you are going to extract from the low energy region, and you expect to get more precision. So to summarize, so the first is we have the existence of exotic hadrons are a consequence of gluon dynamics, and the forward-backward asymmetry in eta pi and eta prime pi is evidence of these exotics. And if you really want to extract the exotic multiplet, we think you are going to need to take into account the radio physics, because you are starting to enter in an energy region where restricting to 6-7 partial waves can be particularly dangerous. You have to start thinking that you need probably to resum all the partial waves. And then you have to think about using constraints that come from the fact that you need to take into account all these high energy physics, all these radio exchanges. And the way that to do that is through the finite energy sum rules constraints. The XYZ phenomena, and this was a summary of the third topic that I talk about. The second topic is XYZ phenomena are yet to be understood. And there may be molecules, there will be compact tetraqubit, pentaqubit states. We want to know, and photon electroproduction can give us a big insight. So running this kind of text and physics cases is important to see what could be feasible and what could not be feasible for the EIC program and for if happens an upgrade of Jefferson Lab. And then regarding the Hsieh radiative, we got the poles for these scalar and tensor states. And now comes the moment to start thinking about what are the nature of these poles. And actually, I don't know if this is known, but our poles are going to be picked up by the particle data group in their next edition. Okay, so thank you very much. That's everything I have, and thank you for your attention.
Yeah, thank you very much for this nice presentation. Are there questions for Caesar? Yeah, Christoph.
Thank you very much for the nice talk. I have actually 3 questions. I want to see how many I'm allowed to raise. The first one, I want to go chronologically through your talk. The first one is about the pi S wave, where you started off from. You say you have a rho component. I would be just curious to hear how you actually treat that.
Oh, yeah. Yes, we don't. It's not really raw component. I mean, you have to consider it's like a third channel that is there to account for the physics that is not put inside pi and kk. So you can think of raw like 4 pions and stuff like that.
But how do you actually parameterize it?
The way it's exactly parameterized in the same way, but we are basically using that raw like as the threshold to start. It's like it's going to substitute this SK, and also it's going to be in this kind of formula.
So therefore, you treat stable rows. Is that what you're saying?
Yeah.
Okay.
I mean, it's like a don't take it as a properly physics channel. It's just like a dummy channel you use to put like, let's call it all the garbage.
Yeah, but the point is that if you have an S-wave threshold for stable states, you get a very sharp onset of that channel, while rho sets on very smoothly, because it's basically 2 pion pairs in individual p waves, which gives a lot of centrifugal barrier factors. Therefore, and it starts at the 4 pi threshold, however, already. Therefore, there is a paper by
one detail.
Let me just finish, please. By Stefan Roperts, Bastian Kubis, and myself, and we parameterized the rho channel in there through a dispersion integral. Maybe you want to look at it and see if this would be an option for you, because a sharp onset of an S wave is potentially dangerous.
Is that going to affect above 1 GeV in this region?
Above 1 GeV. Well, rho you get it actually at the two rho threshold, right? That's
okay. So it's 1.4. Yeah, you're right. Yeah.
Okay.
It can affect.
My next question would be about
one comment. Christoph, yeah, one comment about your question. If you see I mean, it is true that it can be very dangerous because it's a sharp threshold, as you say. But if you see the actual plots, we don't seem to see something really sharp at 1.4 or 1.5. Maybe that deep Caesar is showing right now, but
yeah, maybe here.
Maybe in this case.
Maybe the point is that if you use a parameterization that has a sharp onset in the partial wave that's not actually there from the physics side, and the data doesn't call for it, then the fit will not allow for a large contribution. Because it wants to prevent that sharp onset, and therefore you basically suppress in the fit the 4 pion component, although in principle it might be more important. Therefore, I think it's potentially dangerous to have such kind of artificial sharp onsets in the parameterization, because it might lead to wrong conclusions.
Yeah, I agree with that. I was just pointing out to the fact that maybe in this case, it's not showing up.
Well, it's not showing up the data, and yeah, wrong conclusion, but in a limited energy range, I guess.
Well, once you are well above the rho threshold, it doesn't matter anymore. To that, I agree.
Yeah. So basically, you are saying that we are in danger in this region that we are actually not getting that well. Yeah. Thank you. That's a very good point.
My second question is about you showed these your pole extractions in the D wave and these kinds of clusters, and then you showed there circles where you actually you interpret as certain states, and especially in the D wave plot, there are a couple of clusters that are not encircled. What is the rationale here?
Okay. Well, that is very tricky. That is very tricky. So one of the things that happens when you do this is so you can see also there are like gray curves. You can see maybe you don't see them very well.
Well, not really.
No, not really. No, sorry. But no, the thing is the following. We are using a bootstrap. Okay. So the idea behind the bootstrap is that you can have, well, one thing that you could have in a parameterization of an amplitude are spurious poles. What do I mean by that? I mean, imagine that you have statistical fluctuations in your data, okay? And then you feed your data with one single curve. So how does your model try to accommodate that statistical fluctuation? Because your model is analytical, it can only accommodate that statistical fluctuation through a pole. So if you do one single fit, a chi-square fit, you will say, hey, I have a pole here, I just discovered a resonance. And that's wrong. what we do is we do a Monte Carlo on the data, taking into account all the errors. And that means that if you have a pole that is well established, that is well located, it's going to be stable against that Monte Carlo and that bootstrap. That's what happens. For instance, this is the best case, F2. You can see how everything clusters, everything is beautiful. And then that pole that was due to a statistical fluctuation is going to move like crazy. And it's going to do things like this, like going like here, going here, going here. And that guy is just an artifact of the fact that in order to reproduce that statistical fluctuation, the only way your model has is through a pole. But that's not a resonance. That is artificial. And that's what we call a spurious pole. So here we are being transparent, saying, look, we have this guy, we have these poles. We are not getting just 3 poles, we are getting 4, but 1 is complete noise. So I'm not going to say that guy is a resonance, because that guy is just due to some kind of fluctuations that are in the data.
Okay, thank you very much. And
No,
the final
fine.
question is your when you talked about the double regge.
Okay, yeah. Which slide do you want? Tell me.
Well, any, it doesn't really matter.
Okay.
So just
so
if it
I'm
just
go-
shows a
I'm gonna do
diagram,
here.
it's fine. Yeah. You say this thing is more relevant for final states that contain an eta prime than for those that do not contain an eta prime.
Yeah.
But my immediate reaction to that statement was, isn't that natural? Because after all, the eta prime acquires most of its mass from the UA1 anomaly, which is gluonic. Therefore, isn't that sort of, I wouldn't call that exotic, because you said this points at exotic things going on, but the eta 1 is explained. Therefore, this is not really exotic. But I wasn't surprised to hear you saying that more gluonic stuff goes into the eta primes than into the eta.
Yeah, I'm not surprised either. I mean, this is just confirmation. I mean, think about the following. We are not trying to discover here an exotic, because the asymmetry is there. I mean, it comes from the experiment. What we are trying is, how do I have to model the amplitude to do a good extraction of this beautiful compass data that are coming, and how to do it in the best way to extract the multiplets of exotics. So yeah, it's not surprising at all. I agree with you.
Because I heard you saying when the double regge is relevant, it points at something exotic going on, but then I misinterpreted the statement probably.
Yeah, probably I misspoke. I mean, it's
okay.
I could, but yeah, I mean, it's not unexpected what I'm showing here. Absolutely.
Okay, very good. Thank you very much.
Thank you, Christoph.
All right, so the time's over, and I would like to have the next 2 questions after the break. I hope this is okay for Bernard and Sean. And we will have a break of half an hour to get some lunch, and we will reconvene here at 12:35. Okay, so thank everybody, and thank especially the speakers of this morning session.